Okay, so welcome to today's class. I will be talking about ECG. So this is a very important topic, not only for your MBBS, but even after that. So understanding the basics of this is actually going to help you out a lot. So this is a very simplified version. The very basic things that you need in order to understand the next class where I'll be talking about the clinical aspects of how to apply your ECG in real life. Okay, uses of ECG again is a question that comes usually for the first year students. So that's why I plan to do this particular thing. So the thing about Oracle, we'll just have a brief discussion. For those of you who don't know, Oracle has live class sessions like the one you're attending right now. Recorded classes are there. Notes are there, as well as MCQs, so which are there in different difficulty ranges. Apart from that, they also have a book a slot session where you can get a personalized counseling session as well. Next week, we'll be doing the uses of ECG, and with that, we'll conclude our ECG series. So this are the various subscription plans that are available. You can use this code in order to avail the discount. So without much ado, I'm going to start the topic. So what is ECG? So that is the first thing you need to understand. So you keep any sort of electrode on the surface, and using that, you record the electrical activity of the heart. That is what ECG does. Okay. So using any sort of surface electrode, you record the electrical activity of the heart. Why do we need to do that? So it's as if we are looking at the heart from different points of view to get a three-dimensional model of the electrical activity of the heart. So essentially, in as simple as term as I can describe, that is what ECG does. ECG, if this is your heart, it looks at the heart from all of these different angles and how it looks like this normal condition, how it looks like from these different angles. That is what ECG does. Okay, so I just recap what we did in last class because that is very crucial for you to continue to understand ECG. Okay, so last class we had seen the conductive system of the heart. So when we looked at your heart, I'm drawing the right ventricle, left ventricle. So in your heart like this, initially from the SA node, the impulse goes down. There are three internodal pathways. So this is the directionality in which your ECG, the electrical activity is going to go. And after that, it's going to reach your AV. From the AV node, now it's going to go down. So as it's going down, what is going to happen is the septum, interventricular septum, which is there is a left to right septal activation. And after that, this goes on down where it reaches the apex. And once it reaches the apex, this conductive pathway is going to crawl back down and go to the base of the heart. If you know the anatomy, beneath this part, there is a base which is there. Okay, and reaches all the way to the pulmonary cornice. So this one particular diagram, I want you to understand. Okay, this is for those of you who haven't listened to the previous class. So again, we have SA node, AV node. It goes to the ventricle, where the interventricular septum, left to right activation is happening. It goes down, reaches the apex, where it crawls down beneath it. Okay, so this is the basic with which we have to start to understand ECG. Now, for ECG, you have to understand a term called lead. Okay, so you take one electrode, you take another electrode, you pass it through wire to a galvanometer which can read it. Okay, so this full complex of your electrode, wire, okay, and your galvanometer. This is what you call a lead. So different kinds of leads can be created using ECG. Okay, it's all dependent on what exactly are the two pairs of electrodes that are used. Okay, so this can be done in two ways. You can use what is called a bipolar, or you can use a unipolar. So these are two terminologies about leads you have to understand. So questions of this also comes with exam, where they'll be like differentiate between bipolar and unipolar leads. So bipolar leads, what is going to happen is both of these electrodes that you have, both are going to be active electrodes. That means they have some sort of charge. So if one is positive, clearly the other one should be negative. Okay, so you take two active electrodes, both having a charge, and between them, you connect the wire with a galvanometer. That is a bipolar lead. On the other hand, you take only one active electrode. Okay, and that is mostly going to be a positive electrode. So you take one active electrode with reference to a inactive electrode, not a negative one. It is an inactive electrode. What does inactive mean? A near zero potential. Okay, so a near zero potential electrode is created. So now what will happen? One active is there, the other one is the inactive one, which is almost zero. So in terms of this, what are we understanding? The active electrode is measuring with reference to something that is inactive. Compared to that, how much is there over here? So that is what a unipolar electrode does. Okay, so again, bipolar electrode, two active electrodes are there. In a unipolar electrode, a unipolar lead, what we have is one active electrode and another inactive electrode. Okay, so that is the thing about lead. So now once you create leads like this, for example, you have the right hand, left foot. Okay, so just using this, if you take a bipolar, for example, you keep one in your right arm, you keep another in your left arm. Both are active. Okay, so that will give you one lead. Now you take your right arm with your left foot, connect them using a bipolar two electrodes, then that will form another type of lead. You take this and this, again another type of lead. So like that, you can create different leads. Okay, so this will help you detect your electrical activity. How does it help you detect? That we have to understand. Okay, so before that, one small thing about your ECG that you have to understand: the speed of the ECG and the calibration unit. These two things you have to always check when you get an ECG. Okay, so one thing is you'll see something like this, a symbol like this whenever you look at an ECG. And that is the calibration of your amplitude. Okay, another thing you'll have to check for the speed setting. The speed setting usually is around 25 millimeter per second. So 25 millimeter is covered in 1 second. Just remember this. Okay, so I'll just for you to understand, can you see every ECG at the corner of it, you'll see this calibration unit like this. Okay, so like that, you can see a calibration unit like this. Okay, so that is the next thing that I want you to understand about ECG. So two things, we'll come to that a little more in detail later. This is very important to start to use an ECG. So one is the amplitude calibration. Two is the speed setting. If these things are changed, then the whole idea of how to read an ECG is going to change. Okay, so now that is settled, we'll try to create these leads. What are the different leads? What does it actually tell you? So if you take a look at your heart, okay, I'm just gonna draw a person over here. So now this person, I'm sorry, it's a very vague diagram, just trying to draw it fast. Okay, so this person, what we can do is we can take and keep one electrode here. This is the right side. This is the left side. Keep an electrode on the right arm. Take one and keep it on the left arm and connect them using the galvanometer. This is going to create one lead. Again, I was telling you, instead you put it in the left leg, okay, and connect these two. That is going to be one lead. Instead, connect these two. That's going to be another lead. Okay, so what you have to understand is, so your body is a volume conductor. So just to, simplify this, I'm going to remove all of these points so that it becomes easier for you to make sense of this. So because the volume conductor, actually, this is taking the electrical activity from a particular point over here. This is taking the electrical activity from a particular point over here. Okay, and the left leg also, this is taking the electrical activity from a particular point over here. So ideally, it's the same thing. Okay, that is one thing I want you to understand. So I just again remove this. So same thing can be done by instead placing electrodes like this. Okay, so now we keep electrodes like this, we are measuring the same thing. So this is what we call a Einthoven triangle, named after the person who was responsible for bringing about your ECG signals. Okay, so this is an Einthoven triangle, and somewhere in the middle of that, you'll have your heart. Again, the same diagram that we were drawing earlier. We'll put a heart over here. Okay, so this again is your right arm. This is your left arm. This is your left foot. Okay, again, color codings are there. I'm just not going to waste time on all that because it depends. Different companies have a different color coding system based on which country you are in. Okay, so wherever you are, whenever you're doing internship, learn the color coding that way. Generally, we use a color coding where right is going to be a red color. Okay, so just remember that. And if red is there, yellow is going to be on this side. And then we got your green over here. Okay, sometimes a reference electrode, black is also there. But even if that is not used, we can still make the same thermal triangle. So now that we got a structure like this, what are we going to understand from this? So if you were to connect your left arm and your right arm between that, okay, and you take this as a positive, you take this as a negative. So this is done in such a way because anything that moves towards the positive, any electrical activity that is moving towards the positive will be seen in the ECG as a positive reflection. Anything that is moving away from it will be seen as a negative reflection. Okay, so when we draw the diagram of the lead, we generally draw it towards the positive reflection. The negative side is also there. So if you say lead 1, what it implies is you're connecting your right arm and the left arm, and this is a line towards a positive like this. Okay, and this in vector scale is 0 degree. Imagine a whole circle like this. Imagine a whole circle like this. In that circle, this is the 0 degree. Okay, and this is going to be 90 degree. This is going to be 180 degree. So just think of it as a circle, and in that vector scale, this is the 0 degree. So lead, this is your lead 1. What does it connect? Your left arm and your right arm. Okay. In a similar way, we have your right arm and your left foot. So if you connect them, again, this will be positive, this will be negative. That is going to be your lead 2. Okay, so remember lead. So this is the lead 2. Okay, and this is going to be your 60-degree. And in a similar fashion, if you were to connect your left arm to your left foot, and you'd get a diagram like this. Okay, and that is going to be your lead 3. So these are examples of a bipolar. Okay, all of these are examples of bipolar. As you can see, there's going to be one positive and one negative. In this scenario, positive, negative. In this scenario, positive, negative. Okay, so like that, these are examples of your bipolar limb leads. Okay, so generally, if you look at an ECG, it's going to be like this, which is a 12-lead ECG. So we have a 12-lead ECG now. Okay, so this 12-lead includes what do you call lead 1, 2, 3, which we just saw, which are examples of bipolar limb leads. Okay, now we'll go to another type of limb leads, which is called unipolar. Okay, and beyond that, there's another type, which is your unipolar chest leads. Okay, so this together, so there are 6 unipolar chest leads, 3 unipolar limb leads, 3 bipolar limb leads, making up your 12-lead ECG. So we understood now how to create these. How are these created? Again, this is very essential for you to understand because it tells you directionality of the heart. Okay, so it's very important, especially in MI and all. Understanding this will help you, understand where exactly the problem is in the heart. Okay, so we'll come to that in the next class. Until then, I want you to understand these basics. Again, lead 1 is there, lead 2 is there, lead 3 is there. I hope till now there is no doubts. If any doubts is there, just let me know. Now that these are done, okay, now we can try to create more unipolar limb leads. Okay, but before that, I want you to understand something. How do we get your ECG signal? We always tell this particular graph like this: P, Q, R, S, a T wave. So this is a typical ECG that you get. Whatever diagrams are there in your textbook, that is always going to be your lead 2 ECG. Okay, why does this ECG come out like this? ECG comes out like this because when we look at it from lead 2, so remember what I told you, you look at it from a particular directionality, you look at it from here. Okay, from this point, you're looking at it. So anything that is going towards the positive, okay, in this scenario, in lead 2, this is the positive. Anything that is going towards the positive will be seen as a positive, will be seen as a positive deflection. So let's go back to your heart and its conduction. First, what we saw was from the SA node, impulses go, atrial depolarization takes place, and it goes like this. Now, is it going towards the positive or away from the positive? Here, it's going towards the positive. Since it is going towards the positive, this is going to be seen as a positive deflection. That positive deflection that is happening is your atrial depolarization. After that, there is a isoelectric line where no electrical activity is happening. That is basically your AV nodal delay that is happening here. Once the AV nodal delay is happening, that is the PQ or PR segment. Now, after that, it reaches the ventricle. As I told you earlier, the first thing that happens is your left to right activation, septal activation like this. Now, this is quite perpendicular to your lead. See, this is the directionality. Now, this has come perpendicular to this. So, you hardly ever see this normally. Okay, usually it's seen less than one small box and it's hardly ever seen. Okay, but it's seen is called a Q wave. Apart from that, the next thing that is going to happen is this impulse is going to come down and reach the apex. Now again, which directionality is it following? It is coming down towards the positive side. So because of that, it's going to be seen as a positive deflection. And this positive deflection is much more than the earlier one we saw. That is because ventricle has more mass. So this is going to be your R wave. And after that, what happens? This signal from here is going to climb down and go down like this. And since it's going reverse direction towards the negative terminal, now it's going to be seen as a negative deflection that you see here. Now, this particular point is very important, which is called a J point. So at this point, what is happening? The entire heart, entire ventricle is depolarized. Okay, and no electrical activity is happening at this point. So this is where your ST segment is happening. Okay, so we have your R wave, this is your S wave, and this is your ST segment. No electrical activity is happening. After that, what is happening is now repolarization should happen. Okay, this is ventricular repolarization. Mind you, the atrial repolarization should happen somewhere over here. Okay, but you cannot see it because it's getting masked within your ventricular depolarization. So now this is your ventricular repolarization that is happening. Okay, and that is your T wave. So this is why you usually tend to take your lead 2 signals. Okay, you take your lead 2 signals generally. Now that you understood this and how you get the ECG waveforms, we'll go on to continue understanding the other leads. Just leave it here. You just start off fresh. So again, right. So this is the right arm, your left arm, your left foot. You connect them to your interval triangle. Now, what we're going to try to do is first, it's a unipolar electrode that we're going to make. Okay, so what we're going to do is you have to create a near zero potential. So to do that, we take impulses from here, connect to very high resistance, around 5000 ohms of resistance, and connect it to a central terminal like this. So take high resistance and connect them all to a point in the center. So this particular point in the center will act as your reference, which is your inactive electrode. Okay, now you put an active electrode somewhere here. So you take this as an active electrode. Say this is a positive active electrode. Okay, with reference to your central terminal, which is an inactive electrode. So this is an example of a unipolar limb lead. So again, what is the directionality? This is the positive. So now this is the directionality. Please remember, this was your lead 1. Okay, so this is what we call a VL. And in a similar fashion, if you were to take this as an active electrode, now this signal that you see over here, this is what you call VF. And over here in this direction, that is VR. So this is again your unipolar limb leads. Now the problem with unipolar limb leads is that whatever you're doing, say for example, you're taking your right arm. Okay, the active electrode is this. That same active electrode is also put into your central terminal that we just made like this. Because of that, what people notice is in these leads, always amplitude comes very less. So we try to augment it. What did we do? When we are taking a particular lead, we remove this, create the central point only using the other two. So for example, if we are putting this as active electrode, we remove same from the central terminal and just include the other two. Okay, this sort of a setup is what gives AVR, or augmented unipolar limb leads. Same thing if you do over here. How will that be? You're going to remove this and you're going to put like this is going to be AVL and another one is AVF. So in AVF, what do? We remove this and put here and here to create the central point. So this is an example of AVF. So apart from this, so these signals, what do they give you? We have lead 1, we have lead 2, we have lead 3, we have AVL, AVF, and AVR. So we just got this full directionality in this particular plane like this. Is it 3-dimensional yet? It's still 2-dimensional. Okay, so to make it 3-dimensional, we have to add one more axis like this. So that is why we use your chest. Okay, so what we do is, you around the center of the heart, point is taken on the center, with reference to that center, you're going to put electrodes on top like this. So what will happen with reference to some point in the center of the heart, like this. Okay, so that will give you this directionality like this. So these are your unipolar against unipolar. Unipolar chest leads. Okay, so what we do is we take the fourth intercostal space. Okay, sternal angle, come down, reach the fourth intercostal space, right side of sternum. That is where you put your V1. Same thing you put on the left side of the sternum. That is where you get V2. Okay, so in the fourth intercostal space, right sternal margin and the left sternal margin, we get V1 and V2. And then we put the next one intercostal space down. Okay, so in the fifth intercostal space, in the mid-clavicle line, we put not V3, but V4. We skip one. And then take the center of these 2 points. Over here, keep your V3. Okay, so we keep V3 over here. So this is your mid-clavicular line. And After that, we have to put V5 and V6. So in the fifth intercostal space only, we put in the anterior axillary line, that is going to be your V5. And if you put it in the mid axillary line, that is going to be your V6. That is going to be your V6. So once you put all of these electrodes, what it's telling you is with reference to some point in the center of the heart. This is the positive terminal like this. This is another positive terminal. This is how it is actually measuring this activity. So in this plane, it is measuring its activity. So if you look at it, this V1, for example, it is here towards the right side. We're putting on the right sternal margin. So V1 is going to be in this direction, your right side of the heart. Okay, on the other hand, your V5, V6, they're going to be on the left side in this directionality. Okay, so this is going to be on the right side. These are going to be on the left side. Just like that, even these actually give you a directionality. In your heart, your lead 1, okay, AVL, and your V5, V6 talk about the left side of the heart. What about the inferior side of the heart? You can just take lead 2, you can take lead 3, you can take AVF. This will be the inferior part of it. Okay, if you want to take the anterior septal part, you just take these central ones. Right in the center, anterior like that. Okay, so these are your anterior septal parts. So like that, these leads actually tell you a lot about directionality. Okay, at least this much I want you to understand and remember. Lead 1, AVL, and your V5, V6 are talking about the left side of the heart. Lead 2, lead 3, AVF are talking about the inferior part of it. Okay, and this will be your anterior septal part. I hope till now it's clear. If you have any doubt, please let me know. So like that, now that we've created these different leads, now what we can do is we have to now look at this ECG and try to read the ECG. Okay. So just remember what I had told you earlier. I was talking about the amplitude, I was talking about the speed. Okay. This small box that you see over here, this one small box, that is your lead. This one small division that you see here, that is 1 millimeter. Okay, so you take up 5 such small boxes, that is 5 millimeter. Okay, so if you take from here to here, that is 5, another 5, another 5, another 5. Okay, so like this, if you see 1, 2, 3, 4, 5, that is going to be 25 millimeters. Please remember, this was 1 millimeter. Okay, so 5 such small 1 millimeters make up 5 millimeter. If you take 5 of those, that is 25 millimeter. So this is 25 millimeter. The speed setting of ECG is such a way that 25 such millimeter make up 1 second. So what you're seeing here from this point to this point, this is denoting 1 second time. Okay, if that is denoting 1 second time, how much will this denote? That is going to be denoting your 0.2 second. And how much is one smallest division over here going to tell you? 0.04 seconds. So these values I want you to remember. Okay, so 25 small divisions or 5 large divisions make up 1 second. One large box makes up 0.2 seconds. And one small box makes up 0.04 seconds. Okay, so 1 second of this, 0.2 second of this, 0.04 seconds. This. Okay. Now, apart from this, so this is the duration. On top of this duration, what you're going to need is your amplitude as well. So according to this calibration setting that you see, this is telling that this much is your 1 millivolt. Okay, so this much is 1 millivolt. So that means the smallest division that you see here, that is 0.1 millivolt. This is going to be 0.5 millivolt. Okay, so this is what it means. So when you see a calibration unit like this, that is talking about 1 millivolt. Okay, so just see how many boxes are there. There are 10 small boxes there, if you count it. Okay, so what will be the amplitude of one small box? 0.1 millivolt. Okay, so that is one thing that you can use. So now that all of this is done, now we look into the ECG. When we look into the ECG, we can take a look at the morphology of the waves. Okay, I'll just for now use this lead one. What can you tell me now? If you look at the P wave, for example, P wave here is starting from here, ending here. What do you see over here? Around 1, 2 small boxes are being taken. So for P wave, 2 small boxes are being taken over here. Okay, now we know one small box duration is 0.04 seconds. So 2 small box means 0.08 seconds. So here P wave is how much? 0.08 seconds. Okay, can you try telling me what is the duration of your PQ interval? Not interval, sorry, segment. The PQ segment is again from this point to this point. Again, 2 small boxes, which is again 0.08 seconds. Okay, I want you to again take a look at your QRS complex. Start somewhere over here and end somewhere over here. That is also 2. Anyway, it's 2. That is also 0.08 seconds. Okay, now if we want to take the ST segment from this point over here, it's going on till here. That is around 2, a little more than 2, 2.5 maybe. Okay, so we'll just again take that as 0.08. If you want to look at the duration of T wave from this point to this point. So we have 1, 2, 3, little more than that. Okay, 0.12, a little more than that. So this is how you use the speed setting to understand the duration. So in a quick glance, you can say, okay, 2 division, 2 division, 2 division like that. Okay. What about the amplitude now? If you look at the P wave, tell me the P wave's amplitude in lead 1. P wave amplitude in lead 1 is from here till here. That is hardly one small division. So 0.1 millivolt. What about your T wave? It's starting from here and 1, 2, 3. So that is going to be around 0.3 millivolt. Now, how do we tell the amplitude of your QRS complex? We usually talk about a mean QRS vector. Okay, so again, telling this is going to be easy, so I'll just use this for an example. Okay, so let's just take a look at this particular one. How are you going to calculate the mean QRS vector of this? What we have to do is first take the amplitude from this point on top, how much R wave is there. Then from that point, go down and take how much of S wave is there and subtract them. Okay, so you can just see 1, 2, 3, 4. So 4 means that is going to be your 2 millivolt. Plus we have 1, 2. So around 2.2 millivolt is there on top. When you go down, it is just less than 1 large box. Okay, so it's going to be 0.4. So what is the mean QRS vector? It's going to be 2.2 minus 0.4. Okay, so this is going to be is equal to plus 1.8 millivolt will be the mean QRS amplitude. Again, this is very important later when we come to understand about your ventricular hypertrophy and all that and measuring on this. Okay, so this is the next thing that you can do, mean QRS vector. So now we know about how to use this amplitude and how to use the duration. Okay. Next thing I want to teach you is how to calculate your heart rate. So this again will come as a question for you for the exam, for the practical exam, can be kept as a problem chart. Okay. So again, that is important for you to calculate this. It's very simple. You just have to remember just 2, 3 formulas. Okay. One formula is this. 300 by number of large boxes or 1500 divided by number of small boxes or 60 divided by the RR interval. So these are 3 things you can use. 300 by number of large boxes, 1500 by number of small boxes, or 60 by RR interval. How did we get all this formula? It's pretty simple actually. If you look at the number of seconds that are there in a minute. Okay, we have 60 seconds in a minute. Okay, so in a minute we have 60 seconds. Heart rate is told whatever beats per minute. Okay. Now, in 1 second, how many large boxes are there? We already saw in 1 second how many large boxes are there? 5 large boxes are there. Okay. And how many small boxes are there? 25 small boxes are there. And that actually gives you the answer here. Okay. If you use the 60 seconds for a minute, and in 1 second, how much is there? If you're using this formula, large boxes, there you use 5. Instead, 60 seconds into what do we use? 25 for the number of small boxes. Okay, so again, you don't have to by heart this ever. So 300 by number of large boxes, 1500 by number of small boxes. So what do we do now? We look at your R and you look at the next R. Okay, see how many large boxes are there between them. So we're starting 1 short from here and it's ending also 1 short from here. Okay, so here this is going to be 1, 2, 3, 4. Okay, so 4 large boxes are here. So we take 300 divided by 4. Okay, 300 divided by 4. That is going to be around 75. Same this was 3. 300 by 3 is going to be 100. This heart rate would have become 100. Okay, say this would have been increased to 5. Heart rate would have gone to 60. So just have to remember this 2 points. Your normal heart rate is between 60 to 100. If the RR interval at a quick glance is less than 3 small box, it means it's going into tachycardia. Okay, for any reason, if it is becoming more than 5 large box, it is going into bradycardia. Just give you an example. Can you just take a look at this and try to calculate the heart rate? You just see this is going to be from here, to around here. It's not that clear. Okay. But around here, this is going to be one large box. So the situations like this is where you actually utilize the 1500 formula to get a more accurate picture. Okay. So on top of that, maybe 2 small divisions are extra. So 1500 by how much small divisions are there? Okay. So if you look at it like that, it's actually around one large box. One large box means 300 speed. So this is a tachying which is happening about around 300. Okay, and since it is more than 1, it's going to be less than 300. Okay, so this is again, at a glance, you can just tell, okay, this is very fast. On the other hand, can you look at this? How much do you see a difference? 1, 2, 3, 4, 5, 6, 7. So this is coming to around 40. It's a very slow rate actually. Okay, so like this, at a glance, you'll be able to look at and tell the heart rate. You can calculate also using these formulas that we were talking about. Okay, so again, from this topic, for your exam, the question is going to be unipolar versus bipolar. What is the difference? One. Okay. Maybe part of an essay, one question like what is the lead? 1 mark question can come. Define ECG. Like that. This will be like some questions of an essay. That's okay. Your Einthoven triangle and what we call Einthoven law. I didn't talk about this yet. So Einthoven law is very simple. We have this is lead 1, this is lead 2, okay, and this is lead 3. So at any point, so these are all equilateral triangles. So at any point, if you can get the value of 2 leads like this, for example, you take lead 1 and lead 2. That will be equal. The mean vector of that is going to be equal to this one because it's an equilateral triangle. So that is what Einthoven law tells you. If you get any combination of 2 electrode lead like this, you can get the other one. Okay, so that is Einthoven law. Then your normal conduction, your ECG with neat label diagram and describe the cause of each way. Then again, heart rate calculation. Okay, so these are all various questions that can come for the exam from this topic. Okay, again, a diagram of not that important also, but diagram of these leads also can be asked. Okay, so that is it with regard to your basics of the ECG. Now, how are we going to apply it? What are some clinical scenarios which are required for the exam will be taken in the next class. So if you have any doubt, please do let me know. Yeah, I'll just wait for 2 minutes. Just let me know if you have any doubt, anything you want to discuss with me about ECG or anything from the previous class. Okay, so I guess there's no doubts. We'll call it a day then. I'll meet you next class then, where we'll be talking about the clinical applications of ECG and some clinical scenarios which can come as questions for the exam at your level for MBBS first years. Okay, so see you then.